Hello? Hello? Okay. Okay. Good morning, everyone. I think it's time to start. Okay, so let us continue with the basic dimension agnostic learning setting, and then we're going to proceed to a very powerful classical linear classifier called Supportback Machines. So as we spent quite a while in the last lecture introducing the concept of basic dimension, right? So the motivation of the basic dimension comes from our analysis on the consistent learner and agnostic learning, right? So we did this analysis for consistent learner before. That is, no matter what training data you're given, you always assume you can find a hypothesis which gives zero prediction error on the training set, right? So that basically implies that, okay, your target function must stay inside the hypothesis space. Otherwise, you can always find a training set which differentiates the target concept and any hypothesis in your hypothesis space, right? That is true, ideal. So we then talk about a more realistic setting, which is called agnostic learning. Agnostic learning means that, okay, you can use whatever hypothesis space to search for the hypothesis, right, during the learning procedure, but we do not assume the target concept or target function is inside the hypothesis space. That basically means that you cannot guarantee zero training error, right? Because it is possible that, okay, you're gonna search over this particular hypothesis space, right? But your target concept is here, right? Even the best hypothesis in this hypothesis space won't guarantee zero training error. That is the key to understand the setting of the agnostic learning. But the learning strategy remains the same, meaning that we want to minimize the training error, so that we expect that, okay, although the training error is not necessarily zero, but we still expect our test error or our generalization error could be small. Right? That's our strategy, learning strategy for the agnostic learning setting. Then we also use tail bounds, more specifically the Chernoff bound to show some sample complexity and generalization error bound. Right? So the generalization error bound just give you a brief refresher of mind. So you don't need to memorize the formulas. I cannot memorize formulas as well. But just to give you a sense that the generalization error bound is upper bounded by, the generalization error is upper bounded by the training error plus some term. Right? So you cannot ignore the training error because in the agnostic learning setting, the training error is not necessarily zero. And we found some surprising similarity in terms of the sample complexity bound for both the agnostic learning and consistent learning settings. Right? So we found that, okay, the number of samples required to satisfy the error level, both are dependent on the log size of the hypothesis space, right? So you know that the log size of the hypothesis space actually indicates the capacity or the expressiveness of the hypothesis space, right? So obviously, the larger the hypothesis space, meaning that the more expressive the hypothesis space, you would require more training examples to achieve the same error level, right? The generalization error level, right? And then that brings naturally another question, right? So what if your hypothesis space is infinite? Right? This is not uncommon. Right? So consider just the linear classifiers, which are quite simple model assumption. Right? We assume our receiving function is a linear function, but all the parameters, like the feature weights, the bias parameters, they are continuous values. So in your hypothesis space, you have infinite number choices of those parameters, meaning that your hypothesis space is infinite. And then, how do we construct the sample complexity bound or generalization error bound, like for the infinite hypothesis spaces? That's what motivates the invention of this concept of VC dimension. VC dimension is a kind of tractable and finite way, in most cases finite, to measure the capacity or expressive things for arbitrary hypothesis spaces, right, including those infinite hypothesis spaces. And the VC dimension is defined on the basic concept of shattering. So we used quite a few examples in the last lecture to explain the idea of shattering, right? But now let us just briefly review it. So shattering is talking about a set of functions which we usually refer to as hypothesis space, and a set of points. Right? Those points, you can view them, okay, we know the location of those points, but we do not assume any labels on those points. So we say that our hypothesis space H can shatter this set of points S if for every possible partition of the points in S into positive and negative examples, we can find a corresponding function in H such that it can give exact prediction over those labels. So, give a concrete example. Suppose you want to say, okay, your hypothesis space can shatter 3 points, right? That 3 points, the locations of the 3 points are fixed. But if you want to claim that you can shatter them, you need to consider all possible labels on these 3 points. Each point can be labeled as positive or negative, right? 2 choices. So 3 points, you actually have a 2 to the 3, which is 8 possible labeling schemes, right? So you need to ensure that for every of these 8 labeling schemes, you can find a corresponding hypothesis in H which can correctly predict those labels. That is called shattering. So that basically means this is kind of, if you want to show any set of points can be shattered by your hypothesis space H, it's quite tedious, right? According to the definition, you have to enumerate all possible labeling schemes over those points, and then for each particular labeling scheme, you need to find a hypothesis in your hypothesis space that can correctly predict all the labels under this labeling scheme. So just to ensure everyone understand the key idea of the shattering. Okay. And now, based on shattering, how do we define VC dimension? The VC dimension of a hypothesis space H over some instance space X is the size of the largest finite subset of X that can be shattered by H. So there are 2 critical points inside this definition to avoid you being confused. So first, if you want to claim that the VC dimension of your big H is no less than D, what you need to do is just to find one subset of size D. Show that this subset of size D can be shattered by H. So this is quite a weak requirement. You don't need to show, okay, any subset of size. You don't need to show every subset of size D must be shattered by H. As long as you can find one particular set of size D that can be shattered, you can claim, okay, your VC dimension of H is no less than D, is at least D. So for example, if you want to show, okay, the VC dimension of your classifiers is at least 3. You just need to find an arbitrary set of 3 points. And as long as you can show, okay, this particular 3 points can be shattered by your classifers, then you can claim that your VC dimension is at least 3. It's not necessary to show, okay, every 3 possible locations, they can be shattered by H. It's not necessary to show that. So this is an existence statement. And only when you cannot find any subset of size B that can be shattered, you can claim VC dimension is less than D. Let us use a concrete example again, right? Suppose you want to show your VC dimension is 3. What you need to do is illustrate 2 points. First, you can find a particular set of 3 points, whichever locations you want. And for these 3 points, you show that they can be shattered by your linear classifiers, then your VC dimension has these 3. And then you need to show that for arbitrary 4 locations, the corresponding points cannot be shattered by H, meaning that your VC dimension must be less than 4. And then the 2 conclusions end up with your VC dimension being exactly 3. Does it make sense? Any question? Everyone is comfortable with this? Okay, great. Yeah, because this is a very important fundamental, so I don't want anyone to get confused here or to misunderstand here. Okay, so here I we list several known VC dimensions for common use classifiers in theoretical analysis and in practice. So half intervals, which is a left bounded interval hypothesis space we discussed in last lecture. The VC dimension is simply 1. We analyzed that before. Hey, they can shatter 1 point, but the 2 points left boundary intervals are not able to shatter them, right? And the 3 intervals, the VC dimension is simply 2. Right? We show that for any 3 distinct points, they cannot be shattered by 3 intervals. And half spaces in the plane, which are lines in the plane, right? And we actually have discussed this before. You can shatter 3 points. We list this all possible labeling schemes over 3 points, right? 8 possible labeling schemes. You can take a look here, right? We show that, okay, for every of these 8 labeling schemes, we can find a corresponding line which can perfectly predict the positive and negative examples. But we just leave this as exercise for you guys, right? To show that the lines cannot shatter any 4 points on the plane. So that gives us the result. The VC dimension of the lines in 2-dimensional space is 3. And in general, if you're learning a linear classifiers, right, you can look at the entire space of linear classifiers in a 3-dimensional instant space. Then the VC dimension is D plus 1. And here is the result for neural nets. The VC dimension of neural nets is the number of parameters. So you can see the neural net models can be very expressive, right? The larger the neural network you have, the more the number of parameters you have, and the larger VC dimension of the neural network. Right? And finally, a very simple, very interesting result. This is a non-parametric classifier. It's called nearest neighbors. Right? If you use nearest neighbors to do the classification, it simply look at which training point is closest to the test point and use that label as a prediction. And this dimension for one nearest neighbor is infinite. So it's kind of an interesting result. But anyway, the intuition here is a rich set of functions shatters a large set of points. So you can set that you can view it as, okay, as long as I have a rich set of functions in my hypothesis space, I can expect my my hypothesis space has larger VC dimension. Okay, so we have to wrap up the definition of the VC dimension. So here I want everyone to know the motivation of VC dimension. So the motivation is just to find a good way to measure the capacity or the expressiveness of the hypothesis spaces used by a learning algorithm, because it is important for us to derive or analyze sample complexity and also the generalization error bound. And for infinite hypothesis spaces, you can view VC dimension behaves like a log size hypothesis space we used before. Right? So you can view it as a counterpart when your hypothesis space is infinite. And then someone asked, so now that we know, okay, if you have infinite hypothesis spaces, right, you've got VC dimension, can give you a measurement, right? So based on VC dimension, what's the sample complexity? What is the generalization error bound? Do we have such kind of analysis? The answer is yes. So actually, the derivation of this VC dimension-based sample complexity and generalization error bound are much more complex. You need to use a lot of inequalities, so it's beyond scope of this class. Here we just list the results to give you a sense. But actually, the insight it reflects is the same as we did before, right? Where we assume that your hypothesis space is finite, right? So here is the result for the consistent learning setting. So given a training set P with M examples, I suppose you can always find a hypothesis which gives zero training error, meaning that they are consistent with all the M training examples. And then if the number of training examples is bigger than this lower bound, and then we claim that with probability at least 1 minus delta, the learned hypothesis has the generalization error less than epsilon. So you can see the style of the statement is exactly the same as we did before, right? In a consistent learning setting. The only difference is that in our previous analysis, we require the hypothesis space is finite, right? And then we use log size of hypothesis space to indicate their complexity. Now, we remove this constraint, we allow the hypothesis space is infinite, and then the sample complexity bound will contain basic dimension that measures the complexity or the expressiveness of the hypothesis space. Right? So you can see that sample complexity bound is determined by the designated error level, epsilon, right? And the designated confidence level, delta, right? How likely you want this to happen, right? And also the basic dimension of the hypothesis space. Of course, if you want to achieve a smaller generalization error level, you got to increase M, right? Because you are increasing the lower bound of the samples, right? And you want to increase the chance that you have a small error, right? You actually increase the confidence level. You got to increase the number of samples. They are all reasonable, right? Enjoy the same rationality with our previous analysis. And also you can see that the sample complexity bound is proportional to the VC dimension, right? So this is almost the same as our previous sample complexity bound, right? So under the same level of epsilon and delta, right, the more complex the hypothesis space you have, the larger the sample complexity bound, right? Meaning that you need to use more training examples to achieve the same generalization error under the same confidence. Okay. In other words, using this dimension, our result still favors the Occam's razor principle. Right? Any questions so far? Is this result reasonable to everyone? Okay, great. Yeah, you can just consider this just another version of sample complexity bound, where you use base dimension instead of the log size composite space. And we got similar statement for the agnostic learning setting. But a more important result for the agnostic learning setting is the generalization error bound. Based on the generalization error bound, we're going to discuss how the well-known Supportback Machines were invented. Right? So here we just list the details about the sample complexity bound with this dimension. So suppose we have m training examples. Then we claim that with probability at least 1 minus delta, the generalization error of the learned hypothesis H is upper bounded by the training error of H plus a term determined by the basic dimension, the number of training examples, and of course the confidence level delta. So you can see that because this is under the agnostic learning setting, right, we cannot guarantee zero training error. So if you want to quantify, you want to estimate the generalization error, you need to account for the training error. In addition to the training error, you have an extra term which are controlled by the complexity of the hypothesis space. And also, of course, the number of training examples. So if you want you have a smaller generalization error or true error, right? In addition to reducing the training error, you need to increase the number of training examples, right? So you increase the m, then this whole term will decrease. Right? Although you have a denominator m and numerator is logarithm to m, you know that the logarithm increases much slower than m, right? So you increase m, this term is decreasing. And similarly, if you choose a smaller or the less expressive hypothesis space, then this term is decreased as well. This can be easily shown. You can take, say, derivative of this basic dimension or basic dimension. You can see that with decrease basic dimension, this term is decreasing as well. So this result actually reflects or gives us some guidance. How should we improve the performance of our learning algorithm? Right? So first, you should try to reduce the training error. Right? And second, you can try to increase the number of training examples. This is very intuitive, right? We know that in almost all the machine learning applications, you use larger number of training examples will usually give you better performance. And reflected here is that actually you're tightening the generalization error bound. And similarly, if you can maintain the same training error, but at the same time you can reduce the complexity of your hypothesis space, meaning that you're reducing the basic dimension, you can reduce this term. And then you reduce the bound of the true error, then you expect to improve the generalization performance. Any questions so far? Is everyone good with this? Okay. We do not need to know how this is derived. Right? This is not theoretical class. But we do need to understand the meaning of this generalization error bound. Any question? Okay, looks like everybody's comfortable with this. Okay, great. So now finally I just want to advocate why we should know a little bit concepts about computational learning theory, because it does take an important role in the development of machine learning. Right now, only to play some mathematical games. So, for example, by understanding some theoretical questions, and we can motivate the development of new machine learning algorithms like boosting, right? And also, I'm showing that in general, the true error of the learned hypothesis can be bounded by the training error plus a term determined by the basic dimension. Of course, number of training examples, confidence level. And we'll see in a minute that how this generalization error bound motivates the structure risk minimization principle with the instance of Supportback machines. Okay, so now from today, we're going to spend a few lectures introducing these classical, powerful, and very widely used classifiers called Supportback machines. So Supportback machines were originally proposed as linear classifiers, but later, as we'll see, by leveraging some fundamental knowledge in optimization, we can inject the so-called kernel trait and to make it a powerful nonlinear classifiers. Okay, so someone might be concerned that okay, Supportback machines looks like outdated. The answer is no. So it's very powerful and very popular. It was originally proposed in 1990s. At that time, SVM, or Supportback machines, were viewed as like groundbreaking or breakthrough in the machine learning area. At that time, nearly all people in the artificial intelligence community we were like artificial neural nets are dead. We should switch to SVMs. And that was the reality before. And because they were so powerful, so easy, and also very elegant because it's based upon computational learning theory, right? And but for artificial neural nets, right now, still they're viewed as a magic of tuning. Right? You don't know. Sometimes you don't know why it works so well. Sometimes you don't know why it works so bad. So, but right now, indeed, I mean, the research of Supportback machines is not hot anymore because after the invention of Supportback machines, after 20 years or 30 years research, people have developed like numerous variants of that to improve it in every aspect. There seems not too much new research ongoing, but in the real applications, it's still used everywhere. Right? So the typical scenario where you can apply SVM is that you have a small amount of data, and you don't really have like trillions of data points, billions of data points. Actually, this is pretty common. Although nowadays people often call we are in the era of the big data, but this is not true in many scenarios. Right? Like in bioinformatics, like in seismic research, you actually don't accumulate so many data points. Right? And in some medical applications, you are not allowed to use other data points. Right? You really have like very scarce of data. Now, how do you fully leverage the power of the small data, small samples, right? And to get the best performance? And SVM is one of the best choices. And also another advantage of SVM is that it has very few hyperparameters to tune. It's not like artificial neural nets. You have 1 billion parameters. You have to run on 100 GPUs, and you have to build up a cloud computing environment to run those big models. Right? SVM doesn't need this. Right? And even if you want to tune that, you might need to tune 1 or 2 or 3 hyperparameters. That's very easy and convenient. And also, it is called non-parametric. Well, I'm not going to tell what's the meaning of non-parametric, but you can roughly view it as a self-adaptable. Meaning that it's so flexible. If the data is simple, meaning that, okay, the underlying relationship might be just linear, the SVM will reflect the linear relationship. If the data are complicated, right, like it's quite nonlinear, the SVM can tell you it's nonlinear. It's not like neural nets, like you build up like 10 layers neural nets with 1 million parameters. That basically means if your data is simple, it's very easy to overfit. So it has also many other advantages we don't have time to cover, but this is the several critical advantages of SVM. Here, just a list several popular applications of SVM, like text and hypertext categorization, right? So if you overview some news website or whatever website, they're gonna automatically tag the text. Is often done by SVM. Facial expression classification, right? How can you see the emotion from the face images, right? Cancer diagnosis and prognosis, right? This is a typical scenario where you can't have too many examples. Typically, you only have like 20 examples, 30 examples, like 10 of them are control group, right? How do you predict if this tumor is malign or benign? Okay. It's actually it's very important. It's very, very important. And biomimetics, right? How do you predict two drugs or kind of remote homology? Right? How do you detect them? This is very important to know the hierarchy or classification of different species, right? And seismic prediction, as I just mentioned before, right? How do you predict the time of seismic occurrence? How do you predict the damage after the seismic event, right? And geology, right? How do you predict layer structures on the ground, right? So those are all typical applications. So if you're interested, you can just search in the web, right? Like applications of Supportback Machines. There are many such kind of applications. Okay. So before we go to the detail of the SVM, let us look at big picture, so that we can better organize what we have discussed so far. So right now we're still under the framework or the umbrella of linear models, right? And we can roughly characterize those different linear models in terms of the criteria they evaluate model. Right? Why should we view different linear models this way, right? So we can consider the very first instance perception, right? We have discussed, right? So it is a typical mistake-driven learning, right? So we just evaluate the goodness of the model in terms of prediction on the training data, right? If the current model can correctly predict the current training example, we feel this is a good model. We switch to the next example, right? If it fails, we immediately update the model. So if we look at the criterion or the incentive to update model, they actually just look at the performance in predicting the training data. That's the perception. So obviously, this is a kind of like oversimplified, right? Because we really care about the generalization, right? So even you got 100% training accuracy, that does not necessarily mean that you got 100% test accuracy on the future data, right? So during the training procedure, we would like more to know about what's the performance in predicting future examples. That's why we introduced the pack learning and agnostic learning setting, right? So remember, the concept or the motivation of the computational learning theory is to, based upon the training error, to estimate or to bound the true error or the generalization error. Right? So this will motivate the Supportback machines. So in general, the learning principle for Supportback machines is called risk minimization principle. You can view the risk as a kind of a bound of the true error or the generalization error based on the training error, of course, and other terms like basic dimension, like number of training examples, error level, and so on. And of course, you can develop new learning principles by proposing some other criteria to see if this learned model is good or not. So this is the big picture. Hopefully, everyone is not lost in those details. Any questions so far? Okay, great. So here is the plan for us to talk about Supportback Machines. Right? So we're going to first talk about the training principle. So see that essentially Supportback Machines aims to maximize the margin of the linear classifiers, and we will show the connection of this margin maximization principle and the generalization error bound. You see that maximizing the margin is equivalent to minimizing the generalization error bound. And then, based on this principle, we'll propose the SVM objective function. You see that the naive formulation of SVM objective function is really hard to optimize. Then we're going to use a very important property of linear classifiers to fully simplify it into to further simplify it into a constraint optimization problem, which can make life much easier. And then we'll talk about how to solve this objective optimization of this objective in the primal domain, which we can use stochastic gradient descent. And finally, we'll talk about the dual space of the objective function, which we have to introduce several basic knowledge about optimization. It won't be hard, but it's just a necessary concepts from which we can derive the dual space of Supportback machines. And only when we look into the dual space, you will understand why this is called Supportback machines, and what does the support vectors mean. Okay, so here to motivate the training principle of SVM, I'm going to list this error bound again, right? Just to reinforce the idea. So we know that in general, in any diagnostic learning, right, and we have this probabilistic error bound as follows. Suppose we have n training examples, then we claim that with probability 1 minus delta, the true error of the learned hypothesis H with the training error is bounded by the training error plus this term determined by the basic dimension. We can view the second term as a function of basic dimension, right? As we just analyzed, right, the lower basic dimension gives tighter bound, meaning that it gives a smaller overall bound for the true error. Right? So if we want to improve the generalization performance, how can we do that? We maintain the same training error. At the same time, we seek for the hypothesis space who has as small basic dimension as possible. Right? That's the idea. So now, following this thinking, right, can we apply this idea to for our linear classifiers? But there is one bottleneck. So as we mentioned before, right, if we look at the basic dimension of the entire linear classifiers in a d-dimensional space, the basic dimension is fixed. It's simply d plus 1. So it seems that there's nothing to improve anymore, right? At least in terms of true error bound, right? Because whatever algorithm you're using to learn linear classifiers, as long as you search over the entire space of linear classifiers, the basic dimension is fixed to be d plus 1, and this term is fixed, right? It seems that there's no way to reduce the basic dimension so that we can get better generalization error. And how can we overcome this issue? Right? Any thought?
ignore some of the dimensions?
You mean reduce the input dimension?
Yeah, just say like we're not going to include that feature.
Yeah, that's a very good idea. Although we're not going to talk about the solution in that way, but that's a really good idea. Let us just assume we stick to the original input space. Any other thought? Yeah, we can think of a very seemingly stupid idea. I mean, not as you said. Well, your point is quite brilliant, actually. I never thought about that. But let us assume that, okay, we're going to stick to the original input space. But now that if we search over the entire possible set of linear classifiers, that won't reduce the visit dimension. Why not just restrict my search space into a small subset of linear classifiers? Right? So you can imagine, okay, this is the entire linear classifiers, right? The visit dimension of this big hypothesis space is d plus 1, it's fixed. Why not just pick up one subset of linear classifiers? Right? Inside this big space. And you can imagine that because I will pick a small subset of linear classifiers, then you can reduce the visit dimension accordingly. And if at the same time you can maintain the small training error, your overall generalization error bound will get smaller. That's the idea. It's pretty naive idea. That sounds feasible, right? And now the question is which particular subset of linear classifiers should we choose as our new hypothesis space? And SVM introduces a very interesting idea. You're going to use margin to index those subset of linear classifiers. So now let us first recall the concept of margin, right? So suppose we got a data set which can be perfectly separated by a particular hyperplane, right? Then we can define a margin of this hyperplane for this data set, which is the smallest distance between the data points and this hyperplane, right? So in this case, will be the closest point to the hyperplane will be this black point, right? So the distance to the plane is margin. So now during the training and previously, we actually have analyzed, right? So given the same training set, right? You might have many separated hyperplanes. Like H1, H2, both give 0 training error, right? But intuitively, we believe H1, who has a larger margin, will perform better than H2 in the generalization error. Why?
Because the high density.
Yes, exactly right. We did some qualitative analysis, right? So the smaller the margin, like H2, right, the more likely that H2 is going to pass through the high density regions, right? So you can see that H2 passes through the high density regions for both positive examples and negative examples. The consequence is that, okay, H2 is likely to meet some new example on both sides of its boundary, right? So if a new example, which is positive, appears here, then H2 will make wrong prediction, right? Similarly, if a negative example appears on the other side of the boundary here, H2 will make wrong prediction. Okay. And the chance of these new examples are now low because these are high density regions. Right? On the contrary, if we use H1 to make predictions for the future examples, it is very unlikely that you will have a positive example appear in this side. Why? Because this is not high density regions for positive examples. This is low density regions. So that means each one takes a much smaller risk to make wrong prediction for positive examples. Similar argument applies here, right? So it is unlikely that you meet a new negative example here, right? Because this is a low density region for negative examples. That's the benefit of the large margin classifier. The farther away, the larger the margin, the farther away from those examples, and the farther away your hyperplane from the high density regions. You got a smaller risk to make mistakes. That's our previous analysis. I just repeat to refresh your mind, right? But how do we give some quantitative proof to support this? So this is what we're going to discuss right now. Right? Now, as we just mentioned, right, our idea by leveraging the generation error bound is that we're going to consider a subset of linear classifiers rather than the entire linear classifiers, so that we can effectively reduce the BC dimension at the same time maintain similar type of training error, so that we can reduce the whole error bound, right, for the true error. So now how can we define different subsets of linear classifiers? So here we're going to introduce the so-called data-dependent BC dimension. So suppose we consider two sets of linear classifiers, and each one are linear classifiers that have a margin at least gamma 1 for the training set. And H2 are the linear classifiers that have a margin at least gamma 2 for the training set. So you can see that by using these margins, right, we actually define two subsets of linear classifiers, right? Also, this classifier is determined by the training set because the margin must be relative to some training set, some data set. So if we know that gamma 1 is bigger than gamma 2, then we believe that the entire set of functions H1 is better than H2. Why? Why? Because we just analyzed, right? We believe like a classifier who has a larger margin will perform better, right? So you can see that on average, the classifiers in H1 whose margin is larger than the classifiers in H2, right? This is according to the definition. So we believe H1 is better. Right? Does that make sense? Any questions so far? According to the based on the definition, right? We cannot proceed without understanding the definition. Everyone is clear about the definition of these two sets, right? Two subsets of linear classifiers. They're just indexed by two different margins, right? Okay, next, the theory from the left connects this margin indexed linear classifiers and the BC dimension. Okay, so this theorem tells us that suppose I got a set of linear classifiers H who can separate the training data by a margin at least gamma. Right? That is the H, right? So H consists of all the linear classifiers whose margin at least gamma. Then the BC dimension of H is upper bounded by this. Its minimum value of this R squared over gamma squared D plus 1. So D is the input dimension, which is fixed, right? And R is the radius of the smallest sphere containing data. It's very similar to the R when we talk about the mystic bound theorem, right? If you still have impression, we said R is the maximum length or maximum norm of the input vector. And here R here is CME. So what we can observe? The larger the gamma, the smaller the upper bound of this dimension of h. Right? This actually tells us that the larger the margin you have for your linear classifiers in H, the smaller this dimension of your H. Right? Does it make sense? And remember, when we talk about the generalization error bound, the smaller the basic dimension, the smaller the bound, right? So now we can build up the full connection between the margin and the generalization error bound. If we can index the linear classifiers in terms of the margin of the corresponding hyperplanes, right, then we can show that the larger the margin, the lower the basic dimension of the corresponding subset of linear classifiers. And if you use this subset of linear classifiers for training, you expect to get better generalization error bound. Right? Any questions so far? Does it make sense? Right. This is a very smart idea, right? We know, okay, if we just search over the entire, all possible linear classifiers, entire space which consists of all possible linear classifiers, well, you wouldn't be able to improve your generalization performance, right? So, okay, my strategy will be, okay, I want to reduce the search space. I just want to pick a subset of linear classifiers so that I can reduce the least dimension, so that I can tighten the bound, I can improve the generalization performance. But which particular subset should we choose? The idea of SVM is that, okay, I'm gonna index different subset of linear classifiers by a margin. Right? So we can define all the linear classifiers whose margin at least gamma as one subset, right? So then we know that, okay, the larger gamma you choose, the smaller the basic dimension of the corresponding subset of linear classifiers. And if you restrict your search range over that small set of linear classifiers, you can reduce the generalization error bound. Right? And then you're likely to improve performance. Does it make sense? So this is very important to understand the motivation of the SVM. Although there is a chain of logic, but it's a very elegant idea, right? Any questions so far? Everyone's good? Okay, so now that I want to find a subset of linear classifiers to have as small basic dimension as possible, then why not, when I train my classifiers, I just search the linear classifiers who has the largest margin. If I search linear classifiers who has the largest margin, that means I restrict my search space to this subset of H who has the largest margin. Right? That means I got the lowest basic dimension, meaning that I want to get the tightest bound for the generalization error. And then we expect to get to the smallest generalization error bound. That's why SVM chooses to maximize the margin during the learning procedure. because you're going to restrict the search space to a subset of linear classifiers who have the largest margin. Those subset of linear classifiers will have the smallest basic dimension. And correspondingly, it will make your generalization error bound tightest, right, or smallest. Does it make sense? Okay, looks like everybody is good with that. Yeah, that's really good. I'm happy to see your faces, right? Okay. So now we justify the principle of maximizing the margin in terms of based upon the computational learning theory. Right? But here we talk about this, say, okay, we justify this, but the inventors of Supportback machines, they were motivated. They were motivated. They made a very smart connection between the margin and the basic dimension, and then basic dimension to the generalization error bound, and then they derive this principle. This is a very smart principle. Okay, so now we now know we should maximize margin during the training procedure, but how do we convert this principle into some specific learning objective? That's the next step we should do, right? So before we formulate this SVM objective, right, we need to first review the basic properties of linear classifiers, because this is very important to make the objective function easier to deal with. So remember, we got linear classifiers, right, which are determined by the feature weights and bias parameter. And if you want to make predictions, we're going to calculate a decision function, right, which is linear function. Linear combination of the input features plus bias parameter. Then we look at the sign, right? And the classification boundary, or sometimes it's referred to as a hyperplane, is represented by an equation, right? The equation is simply the decision function being 0. Right? And from the geometry, we know that if you want to calculate the distance between any point and this decision boundary, what we need to do is that, okay, in the numerator, we just substitute the coordinates of these points inside this decision function, right? We take the actual value, then divide it by the norm of the width, right? W1 squared plus W2 squared. So this is just the formula, just apply the formula to calculate distance. And another very, very critical property for linear classifiers is that we actually do not care about the magnitude of those W1, W2, B. You can skew them to arbitrary positive scalar, to 100, 1,000, 1 billion. It doesn't matter, because they all represent the same linear classifier and the same classification boundary. Right? So they are equivalent. In other words, if you use all possible W and B to represent the linear classifiers, they are kind of redundant, right? Because for specific W, B, W1, W2, right, you have an infinite number of equivalent choices of B, W1, W2, which represent the same classification boundary, same hyperplane, right? This is extremely important for us to simplify the SVM objective. Let's just keep it in mind. So let us first use a very naive way to formulate our learning objectives. Right? Remember, our goal is to maximize the margin. Right? And of course, to maximize margin, we should be able to calculate the margin. Right? According to the definition, margin is the distance of the closest point from hyperplane. Right? That means for any WB, right? For any current linear classifier, to calculate margin, we have to solve a minimization problem. Right? We need to calculate the distance of every training example xi and yi to the hyperplane, right? And then we pick up the smallest one. And remember, because we assume that our linear classifiers can correctly predict all examples. So the numerator can be simply written as product between the ground truth label and the decision score, right? So know that if you can correctly predict xi, then this product is always non-negative. Okay. So you don't need to take absolute value in front of the prediction score. Okay. So this numerator, this original distance is really called geometric margin, because geometry, we know that it is the distance between this point and this target point, right? But if you look at the numerator only, this product yi times the score is usually referred to functional margin. So we will use functional margin intensively when we talk about the formulation of SVM objective. So now that after we get the margin, we want to maximize the margin, right? So that means we have actually to solve a bi-level optimization problem. In the inner level, given the current model parameters, we need to go through every training example to solve the margin, right, which is the smallest distance. And then in the outer level, we need to adjust WB to ensure that this margin is maximum. That's a straightforward formulation of the SVM objective to reflect margin maximization principle. Okay. Any questions so far? It's pretty straightforward, right? Unfortunately, this is easy to formulate, but it's very hard to compute. Why? Because you have to solve a max-min problem. It's not a maximization problem, it's not a minimization problem. So I can tell you, even if you can solve it, the optimum is not a maximum point, it's not a minimum point. It's called a saddle point. And every time, if you want to update WB a little bit, you have to go over all the training examples to calculate the margin first. So it's very tedious and very costly. So naturally, people would ask, can we simplify this problem? I don't want to deal with a max-min problem. I just want to deal with a minimization problem or maximization problem. This max-min is really weird. I don't want to touch it. How can we simplify this? So here's the key idea. So as we mentioned, if we use the entire possible values in WB to represent linear classifiers, it actually contains redundancy. Why? Because we do not care about the magnitude of those W and B, right? You multiply any positive scalar, it corresponds exactly the same linear classifiers, right? You can multiply B, W1, W2 by 0.1, by 10,000, by 1 billion. They are the same. They represent the same linear classifiers. Now that it is redundant, why should we make our search space over the entire choices, possible choices of WB? Why not we just restrict them to be a small subset? But what subset of WB should we use? And here, we're going to choose the space of WB such that the inner minimization of this numerator is simply 1. So before we talk about rationality, if you assume, okay, if the minimization of this numerator is always 1, across all the training examples, then actually we do not need to solve the inner minimization problem, right? Because remember, to calculate the margin, we essentially to minimize the numerator, right? The denominator is the normal W, it has nothing to do with the training examples. If you assume, okay, this minimization of this numerator is always 1, actually, your margin is simply 1 over the normal of W, right? And you only need to solve the maximization problem. You can actually ignore the inner minimization problem. You do not need to go over all the training examples. That is the big advantage, right? We actually get rid of the inner minimization problem. Then the issue is that why can we restrict or constrain that WB such that the minimization over all the training examples, this functional margin is always 1. So you can view like in this way, right? For arbitrary WB, well, of course, it's not necessary that the minimization of this functional margin is 1. It might be 3. Right? And then when I divide WB by 3, what's the minimization value of the functional margin? It becomes 1, right? Does it make sense? And W3, B3, B over 3, W over 3, B over 3, it corresponds exactly as equivalent classifier to WB, right? So you do not lose anything by using W over 3, B over 3 instead. Does it make sense? Like for any WB, any free WB, right? We cannot guarantee the minimum value of this yi W transpose xi plus b is 1, right? But if we can divide WB by the corresponding minimum value, actually the minimum value is 1, right? And after dividing, they still get equivalent linear classifier. Let me write on this. Maybe better to write it down. Oops. Okay. Well, here is the whole space of WB, right? Free WB. Okay. Of course, for the whole space of WB, we cannot guarantee, well, this minimum functional margin over the training example is 1, right? But now we just want to restrict WB in the subspace. In any inside this space, we require that the minimum value is simply 1. Can you see clearly? This. We restrict our search space to be this, rather than the entire space of WB. That's the idea. So maybe this is not very clear. I mean, this space just requires that for every training examples, your functional margin is simply 1. This minimum functional value is simply 1. This is how we define the subspace of WB. And then we want to learn WB just from this subspace, rather than entire space. That's the idea. But people ask, okay, what if I got some optimal WB? The WB is W star and B star, which is inside here. Do we lose this optimal WB here? That's our concern, right? But here I can tell you, no. Why? Suppose you search this entire space instead, you got optimal value of W star, D star. Well, maybe your mean value of the function margin is 10, right? Probably I just write down a random number, right? Maybe it's 10, right? And then I can immediately divide W star and B star by 10. I got a new pair of W and B, right? And this pair must be inside this small subspace, right? Why? Because if you just replace W star and B star by W star over W star over 10, B star over 10, and this value must be 1, right? It's just like you divide both sides by 10, right? And then your new pair of W star over 10, B star over 10 is inside the space, right? So that means you can just search inside the small space. You can get the equivalent linear classifier as W star, B star. Does it make sense? Right. As we just mentioned, right? Because if you use the whole space of WP to represent all possible linear classifiers, they're redundant. Because you can scale any WB by arbitrary positive number, they correspond to exactly the same classifiers. Why would we need to search over the entire space in WB? You just need to look at a small subset. And this small subset have already covered all possible different linear classifiers. Okay. That's clear. Okay. Let me repeat the rationale again in case someone didn't catch it. But imagine that, okay, if you don't believe my simplification, right? You still want to search over the entire space. You got some optimal W star, B star by using that naive max mean optimization problem. So of course, inside this big space, your minimum function margin is not necessary to be 1. Suppose it is to be 10, right? Suppose it is to be 10. You can take it to 100, whatever you want, right? Just random number for illustration, right? And now if I divide this optimal W star, B star by 10, right? We immediately get that the minimum value, the minimum function margin by using W10 over W star over 10, B star over 10 to be 1, right? This is equivalent to dividing both sides by 10, right? Just you can do it by 10, right? That means if you use W star over 10, B star over 10 instead, your minimum function margin is 1. That means this W10, W star over 10, B star over 10 is inside this small subset we just defined. So W star over 10, B star over 10 is totally equivalent to W star and B star. Right? They're the same linear classifier. In other words, we can just search over this small subset without losing any optimal linear classifiers. Okay? Right? I mean, if you still have some concern on that, you can try to draw this big circle and small circle and look into the definition. You'll see it's pretty easy. It's pretty easy to understand. Okay, so now the advantage is that, okay, we restrict our WB space into a small subset such that the minimum function margin is 1, then we can reduce the minimization procedure. Right? And we need to care about the maximization of the procedure in all steps. And the gamma, the margin is by default 1 over norm of W. That's the idea. So now, if you want to express this idea in terms of formal learning objective, it will be like that, right? So first, our objective now becomes maximizing 1 over norm of W, right? It is equivalent to minimizing the square norm of W. Okay? Maximizing 1 over norm of W is equivalent to minimizing square norm, right? And we put half, a factor half in front of it just for convenience. If we take gradient in front of it, well, you got factor 2, right? It cancels with half. And also, as we mentioned, right, we want to restrict WB in a small subset such that the minimum function margin, this part, is 1, right? That is equivalent to requiring that for every t example, this function margin is at least 1, right? So this is our constraint part. So first, the objective part is half W transpose W, which is equivalent to minimizing the square norm, right? And minimizing square norm is equivalent to maximizing the inverse of the square norm, or inverse of norm. And then we need to list a set of constraints. Each constraint corresponds to one particular training example to ensure that the function margin is at least 1, right? So the minimum function margin across all the training examples will be 1. That's how we formulate this learning objective. So this formulation is called hard Supportback machines. Why is it called hard Supportback machines? Because if you look at the constraint, right, we require that every training example, I, the function margin, namely the product between the ground truth label and this score, is at least 1, right? So it requires that not only this function margin is positive, right? It must be no less than 1, right? So if you require all the 20 examples, this function margin is positive. What does that mean? It means we must correctly predict that example, right? So while I comes to decision score, non-negative means that we correctly predict that example, right? So from the constraints, we can see that we not only require every example to be correctly predicted, but also this skill must be at least 1, right? This is a very strong requirement, right? It requires the data to be linearly separable, and also you need to find a good classifier who has quite a large margin, right? So, unfortunately, you cannot always expect your training data is linearly separable, right? If your data is not linearly separable, you see that these constraints won't be satisfied, meaning that your feasible region is empty. You cannot solve that problem. This is quite unrealistic formulation, right? You cannot assume the data is always linear separable. We know that the data can be almost linear separable or just non-linear separable, right? And we want our Supportback machines can be applied to all kinds of problems, not just for this ideal one. That means to be practical, we need to adjust our formulation in a more flexible way, which we refer to as a soft SVM. We're going to talk about soft SVM next Tuesday. Thanks. I'll stop here.